Yes, sir.
Okay. So what you studied in electrostatics?
The first chapter.
Yeah. So tell me till where you studied?
Sir, I just practiced questions, sir. I wanted to see how much I remembered.
Oh, you are able to solve or you are stuck somewhere?
I'm able to solve, but then I'm making very small mistakes, like and for an MCQ option, because the MCQ options are very similar. Instead of getting 5F, I got F by 5, and I
Oh,
put that option.
okay.
I understood the entire theory, but I just need to practice my questions.
Okay, okay. So now my simple question is, right, like charges, what happens to like charges? Repel or attract? Repel, right? Okay, correct. And unlike charges,
Attract.
attract. Very good. Now the question is why?
Why? Force of nature, maybe because opposites attract, and
No.
repulsions, portions, and like charges repel because maybe as they are similar charges, they have the same amount of charge and energy, so they repel each other. I don't know.
Okay, it's okay because many people don't know. Even if you ask some professor also, they will end up saying something else. Okay, but the reason is very beautiful. Why this happens is because in the nature there is one strong statement I'm going to do here. Like in nature, no, this is very important. In nature, potential energy of a free system always minimum. What I am trying to say is, have you done that experiment? Like you take some soap, make some froth, and then if you just take one thread in any shape, a closed thread, you keep it inside, then slowly it starts taking a circular shape, right? Have you done this? Or for example, if I take one block up and if I just release it, again it want to come back to its same state, right?
Yes, sir.
Are you understanding?
Yes, sir.
So yeah, so I think everyone has joined. Samhita, Shreyuta, Seven. One more Samhita has to join. So I will just explain this reason and we can start the class. Okay, this is just for your information. So guys, any free system in the universe will always try to minimize its potential energy. Okay, for example, if I take a ball, okay, and a ball, and if I displace it little bit, it will go like this, like this. Finally, it comes to zero potential energy, right? Same in case of a ball, if I take it up and release a height, if I raise it by height h, its potential energy will be how much? Mgh, right? If I release it, again it want to come to zero. Correct. So always if there is a free system, it will always try to minimize its potential energy. So in case of charges, let us say we have two charges q1 and q2 separated by distance. We don't know what is their sign, okay, and we don't know whether they attract or repel, but we know that every free system will try to minimize its potential energy. Okay, so here these two charges are free, they can do anything they want to do. We are not forcing them, we are not holding them, so let them do what they want to do based on the law that potential energy is always minimum for a free system. Now what is the potential energy in electrostatics? K q1 q2 by r, right? Correct? Samhita, correct, right?
Yes, sir.
Yeah. So if you want to minimize this potential energy, the separation has to be
Minimum.
More, right? If this is more, then this becomes less, correct?
Oh, yes, sir. Yeah.
Yeah, that's why like charges repel. Understood? If I take one is negative, then this becomes negative, correct? Now, if I want to decrease this, I have to decrease this also. Understood? Because now it is in negative. That's why unlike charges attract. I hope this is clear to you. Okay, we'll
Yes.
discuss about it when I teach you guys electrostatics. Okay, I think everyone has joined. Let me start the class. Hello everyone. Hello Zevion, Shrita, Samita.
Good evening, sir.
How you guys are doing?
Good evening, sir.
Okay, so let us start the class. Before I start, I think you peoples are not answering my questions quickly. I am feeling like you have little bit of lagging in concept clarity. So I just want to revise whatever I have covered in quickly. Okay, guys. So see, when I keep, let's say this is my table, and when I am keeping a block on the table, okay. So you should not look at this like simply a table and a block is kept on that. I told you, right? These normal forces, all these are electromagnetic forces. So you zoom it here and you see what is happening. If you see, actually what happens is inside there are atoms, right? And it is like they are connected like a spring. I'm showing you how inside microscopically, if you zoom it, how things look like. If you observe things in this way, then the life becomes easy. Something like this. These are all atoms, okay? And assume that they are connected by a bond which acts like a spring, okay? If you stretch a rubber band, what happens? It want to come back, correct? Because you are trying to increase the stability distance between two atoms, but that is not their stable state. They want to come back again. So now you guys tell me, if I keep a block on this, what happens? Microscopically tell me what happens. If I keep this diagram, whatever I'm drawing is microscopic, okay? If I zoom it microscopically, these are the atoms
Excuse me,
on
sir.
the
Your screen is not visible, sir. Like, I can't see what you're sharing.
so no one is informing, huh?
So I thought it was a network problem, but yeah, your screen is not visible.
Oh my god, I was not
I
sharing
th
actually.
I thought that you were just giving random summaries, sir. So that's why I was like, okay.
Thank you, Xavier. Thank you. I think you should see my screen now. You're able
Yes,
to
sir. Now
see?
it's visible. Now
Yeah.
it's visible.
So what I was trying to say is this is my table, okay? And this is a block which I kept on the table. Now if I zoom this area, right, where the block is in contact with the table. So inside it looks like this. I have drawn here, okay? There are some atoms, okay? Because everything is made up of atoms and they are connected by bonds which act like springs, okay? Okay, guys. So now tell me, if I keep a block on this surface, what happens? What happens? What happens to these springs? They will contract, right?
Yes, sir.
Yeah, so microscopically, this is what happening. There is a deformation is happening. So this surface will bend like this little bit, okay? Because there is a compression of these bonds is happening. So if that is happening, what the spring will try to do? Xavier, what the springs will try to do?
So it will try to push it back, no?
Exactly. it will try to push it back. So that is why we say that is normal reaction. Understood?
Yes, sir.
Yeah. And similarly, like even if I see this block also, its surface also has that atoms and springs, right? Correct? Correct, guys? That means this block, this surface, this table is also pushing it, and this block will also try to push it back. So that's why same amount of normal is being applied by the block on the table. Correct? These are action reaction pairs. You understood why these are action reaction pairs? There should be very much clarity in this concept, okay? No one will teach you this. So please interact, talk while I am explaining. Now, if you see, observe carefully, the force kind of looks like this, okay? The spring force, because the surface that has bent, no, it is like this. That's why the net force, net contact force is coming like this. So it has two component. One we call normal, one we call friction. Any doubt here?
No, sir.
No, sir.
Okay, so always now whenever you see a question, you have to think like this. Why this normal reaction is coming in the picture? So actually microscopically, this is what happening. Understood? Okay. So that was about this, why these normal forces and all, how they come into picture, and friction, how it comes into the picture. I wanted to explain. Now, we have started studying friction also, correct? One by one, tell me how many types of frictions are there, guys?
Static friction.
Static and
Uh,
Kinetic.
what is the range of static friction, guys? From 0 to mu s times n. Okay, and fs and mu n are perpendicular. Okay, remember this. Always mg equal to not n. We have seen those cases, right? We're pushing a block against wall, correct? In that case, the normal was this. What is the value of kinetic friction? Xavier?
So it will be greater than 0.
It will
Like,
be mu k times
mu
n.
k.
Okay.
Okay.
It will be either 0 or mu k times n. It don't have any range like Fs, static friction. Why
Okay,
the
sir.
static friction has a range, Shreita? Why we say that static friction has a range? Quickly tell me. Shreita, are you there or not? Shreita is not there? Yeah, she is not there. I think she might be having
Yes,
a
sir.
technical problem. Yeah, Samhita, tell me why the static friction has a range. She came back. Shreita,
Sir, can you hear me?
yeah, what is the problem?
What, sir?
You have any network issue?
Sir, my mic wasn't able to unmute. I don't know why it happened.
Okay, I'm asking why static friction has a range.
Sir, I'm not sure.
Because it acts accordingly, right? Depends on how much force you're applying, correct? It has a maximum value, it cannot exceed that. So if you are applying a force less than that, it will be equal to that force, correct? We discussed
Yes,
this.
yes.
Yeah, so we discussed this. I don't want to discuss it again. So that is, see, most people have confusion in friction. So this is the confusion people will be having: how static friction acts, what is the range, how kinetic friction acts, what is the value. Okay, clear?
Yes, sir.
Let's go ahead. All right, guys. Then now tell me, let us say, always see the objects as I explained in this. Okay, this microscopically you have to think in that manner. Okay, so now tell me, based on that thinking, tell me, let us say I have one block, okay, of mass m and another block of mass small m. This surface is rough, that means there is a friction. Surface is rough. Okay, guys, tell me, if this is moving in this direction with velocity v, what will be the direction of friction on capital M? What is the direction of
So is it like on the opposite side?
friction on capital M? This is a small m, this is capital M. Tell me, think microscopically.
So will the friction be like on the opposite side of the direction?
Opposite side of the direction of what?
Like opposite side of the velocity, like
That you think again. Think it microscopically, take your time. See, every force exists in pair, right?
Sir, is it downward direction?
See, either it has to be in this direction or in this direction, okay? Don't
yes,
use
sir.
down up.
So is it along the V, like parallel to V?
Yes, it will be parallel to V. Because see, guys, I'm asking the direction of friction on this capital M, right? If you see microscopically, what is happening? What is happening, you tell me? This, because this capital M is putting some, deformation on the small m, right? So the small m will try to push it back. So it is like the surface has curved like this, correct? So the net force comes in this direction, correct? Now, one component of this will be friction, correct? One will be normal. So the direction of friction on capital M will be in this direction. If you see small m, velocity is in this direction, the friction will be in this direction. And these are action reaction pairs. Any doubt?
No, sir.
Understood, right?
Yes, sir.
Okay. This is important. In which direction the friction is acting, very, very important. So one more example, if I take, let's say you are walking on ground, okay? Not good at drawing. Something like this. Tell me, what will be the direction of friction on the legs? What will be the direction of friction?
So it will be backwards, no?
So see, what you are trying to do, you are putting some force and trying to go ahead, right? You are putting some force on the ground, pushing it yourself, back and trying to move ahead, correct? Am I correct? So you think
Yes,
like,
sir.
yeah, so you think like, well, I want to check the direction of friction on the legs, so I will only see the legs. Okay, so if I see the legs microscopically, if I see the leg microscopically, so the springs are like this, correct? The atoms, because we are pushing the ground like this, and we are trying to go ahead, correct? So the force the ground is applying on the legs will be in this direction, correct? So it has one component in this direction, one component in this direction. The friction will be in this direction on legs. On ground, it will be in the opposite direction. You should have, see, these are advanced level things, okay? These things will be asked in JEE advanced type of exams only. So it's simple, right? You are getting what I'm trying to say?
Yes, sir.
Yeah. So you check, well, so if I want to check the friction direction on my legs, I will see, well, the ground is applying the force on me in which direction? Where my leg springs are contracting in which direction? Okay, that you decide and you see, right? The force will be from the ground, the spring force on your legs will be in this direction only. Then this will be friction, this component will be normal. Correct? And you know, if I tell you draw the free body diagram of this guy who is walking, you will say, well, mg is acting down, normal is acting up. Now your decision is whether the friction is in this direction or in this direction. That depends on whether the contact force is coming like this or like this. Okay, little bit advanced things. Think, spend time. You have to think and you should get a clarity. And even if you're not getting clarity, come to me. All right. Simply, if I say, well, like if I say any object is moving, then friction will be like this. And if it is moving on some ground, on ground, the friction will be in this direction. Okay. Again, if I say a car, okay, if I say a car here, you have to be careful. Okay. Let's say the car is moving in this direction, V. Okay. Then, because these wheels are rotating like this, right? Correct? These are rotating like this, correct, guys?
Yes, sir.
So if they are rotating like this, they are trying to push. Again, it is similar to your legs, correct? So again, here also the friction will be in this direction. So this is interesting things. We study about this more in rotational motion. Okay, let us just continue our simple things. All right, so today's main topic is inclined plane. Okay, inclined plane we'll study. What is inclined plane? You already know. This looks like this with having some angle theta. This is 90 degree. This is 90 minus theta. How to analyze inclined motion? So always assume, so wherever you are standing, right, you assume that to be as x-axis. So what I will do is, I will assume the inclined plane itself as x-axis. So I'll assume this as my x-axis and perpendicular to that y-axis, right? Because if we are sitting on ground, we always say this is my x-axis, this is my y-axis, right? Similarly, now you are sitting on incline, so inclined surface will be x-axis, perpendicular to incline will be y-axis. Any doubt?
No, sir.
No. Let's say I will keep a block here and we want to see its free body diagram. Okay. So if we see the block, the mg is acting down, correct? Correct, guys? Now, this is my mg and this will be my normal, correct? Okay, let us say this block is at rest. That means there is some friction is also acting, correct? Now what you have to do is you divide all this component in x and y direction. Remember, x is this, y is this. So I will tell you the some trick like this is also theta. Okay, if this is theta, this theta, you need to remember simple geometry. This component will be mg cos theta and this component will be mg sin theta. Okay, guys. So now you tell me if this block is at rest, that means the x component of forces and the y component of the forces should be equal. So the friction is equal to mg sin theta and normal is equal to mg cos theta. Okay. So now if I divide these two, f by n is equal to tan theta. Correct? Now f can be written as mu times n, correct? Divided by n is equal to tan theta. And that means tan theta is equal to mu. So if anything is rest on the inclined plane, that particular angle is called angle of repose. This theta is called angle of repose. In question they ask directly, okay, what is the angle of repose? From here you can say theta is equal to tan inverse of mu. Any doubt? Parallel to inclined plane mg sin theta, perpendicular to inclined plane mg cos theta. That's it, you need to remember.
Okay, sir.
No doubt, guys.
No, sir, no doubts.
Okay, very nice. Shall I proceed ahead? Let's say there
Yes,
is a there is a inclined plane and there is no friction, okay? And if I keep a block M here, this is a fixed wedge, okay? Fixed inclined plane, it is not moving. Okay. Now if I release it, if this angle is theta, you guys know that this component will be mg cos theta. This should be on your fingertips, okay? Quickly you should say mg cos theta, mg sin theta. And this is my normal, correct? Now tell me, normal will be always equal to mg cos theta, correct? So these are balanced, so it cannot penetrate and go inside the inclined plane, right? Now it can have only tendency to move in this direction. So what is the net force on the block? The net force is nothing but mg sin theta. If I want to calculate its acceleration, you divide f net is equal to, I can say m into a, it's equal to mg sin theta. From here a is equal to g sin theta. Got cancelled. Any doubt? Any doubt, guys?
No, sir.
no, sir.
Okay. Let us consider friction also now. Let us say there is this inclined plane angle theta. Okay, I'm releasing a block of mass small m. This is a fixed wedge. And there is a friction mu. If I show mu, that means there is a friction. All right. So here, let's say the block is moving. I'm saying that the block is moving. So this will be my normal. This will be my mg cosine theta. This will be my mg sin theta. So what will be the direction of friction, guys? It will be opposite f. So from here, can I say if the block is moving down, so its acceleration will be a. What is its net force? So this force is trying to pull it down. Friction is opposing it. So the net force will be mg sin theta minus f. Correct? What we do, because this is my x, this is my y. So in y direction, all the forces are balanced, normal and mg cos theta. Only in x direction, I am writing sum of force equal to m into a. Okay. F In x direction, I'm writing as m into a. Correct? So mg sine theta. Mg sine theta minus what is f? Mu into n. Correct? Ma. Mg sine theta minus mu into what is n? From this diagram, what is n, guys? It is mg cos theta, right? Is equal to ma. M is gone. G sine theta minus mu cos theta is equal to a. Since it is moving, we consider it as a mu k. Okay. Note it down. You guys understand Hindi?
Yes, sir.
The Hyderabad peoples?
Yes, sir.
Yes, sir.
You guys can speak also, right?
Yes, sir.
Xavier, from where are you basically?
So like I was basically born in Kolkata, and like I've shifted a lot of cities.
Oh, you are Bengali?
Yes, sir.
Okay, okay. Nice, nice.
Thank you, sir.
What do
Was
you
even in
say?
Hyderabad.
What?
Like I was even in Hyderabad for 4 years before coming to
You
Bangalore.
Bengali peoples, na, you go everywhere. Apart from Bengal, you people go everywhere. Bangalore, Mumbai. In Bangalore, also, most of companies, around 30-40% Bengalis are there. Very talented peoples.
Thank you, sir.
I'm expecting same from you, Xavier. A good job.
Yes, sir.
Okay, all right. Noted, right?
Yes, sir.
I don't know whether you peoples are noting it down or not. Okay, anyways, let me start a new topic, constrained motion. Constrained or constraint, sometimes people say constrained motion. What is constrained motion is basically, well, something, see, for example, if I have two bars like this, and if I release a ball, it has only one way to move, right? It can go like this only, it cannot go out, right? So we are making this ball a constraint that it should move only in this direction. Understood? That is the meaning of constraint motion. First constraint we have is a string constraint. String constraint. What string constraint say is, if I have a string, okay, if I have a string, okay, string, rope, anything you can say. What it says is that if I, let's say the velocity of this is in this direction VA, and this point is A, this point is B, and this velocity is VB, okay? Let's say this angle is theta and this angle is also theta. Or I can say alpha and beta, some different angle let us take, okay? So now, guys, what will be this component? VA sine alpha. And what will be this component? VA cosine alpha. Now, here VB cosine beta and VB sine beta. Forget about the perpendicular components, okay? Forget about these two. Just observe the horizontal components that A of H. VAH means horizontal component velocity of A. That is VA cos alpha. And VB horizontal is how much? VB cos beta. Now you guys tell me, if this string, if this is the condition, like you are holding a string, let's say, and you are running with some speed. Okay. So what should be the condition between these two? If the string is not breaking. Let's say Shreyuta is holding this end. Samhita is holding this end. Okay. And they are running and the string is stretched. Okay. The string is stretched. Now, if the string should not break, then what should be the velocity of Shreyuta and Samhita? You're trying to imagine the situation?
Sir, equal?
Yeah, it has to be equal. Otherwise, if Samhita is running very slow and if Shreyuta is running very fast, she will break the string and she will run away with that broken part. Correct? So if the string should not break, in that case, VA cos alpha should be equal to VB cos beta. Okay, what this constraint says is velocity of each particle along the string is always same. This is very important statement. Note it down. This you put heading string constraint. In that you write velocity of each and every particle of the string along the length is same. Along the length, which is important. The component of the velocity along the length is always same. Okay, guys. Noted. Any doubt here?
No, sir.
Okay. Let's take an example. Let's say there is a block which is moving with some velocity v and there is some pulley kind of thing. I will explain all this pulley and okay. And there is one more block which is on ground. Okay. And let's say this angle is 37 degree and this velocity is 100. Okay. Now you guys tell me what should be v. See, if this is v, if this block is moving with v, then each part has to move with v. Correct? Everything has to move with v. Correct? Any doubt?
No, sir.
No. That means this velocity component along the string should be v equal to v, right? What is the component of this 100 along the string? 100 cos 37, right? That should be equal to v, because if they differ, then the string will break. Sometimes what people do, they make v cos 37 degrees equal to 100. That is wrong. Now what you are doing, velocity along the length, you are breaking in some other direction. No, you should not do that mistake. Velocity of the object along the string you should take. Okay? Don't do this mistake. This is blunder. Everyone is clear with this?
Yes, sir.
Okay, all right. Let me ask you guys one question. This is a standard question of H.C. Verma. See, we are pulling this, both the strings on both the direction with U, okay? And the block is moving up with V. Tell me the relation between V and U. Fast. Use the same concept that I told you. Akka 1 cup tea ಮಾಡಿ. Yeah, guys, I came back. I had some work. Tell me, what is the relation between V and U? Come on. Use the statement I told you just now. All of you,
Yes, sir.
tell me the answer. Tell me anything you are feeling. Yes. Shreyata, what is the answer?
Sir, I'm not sure.
What are you feeling? That means you did not understand whatever I taught you so far. Samhita, what are you feeling?
So even I'm not sure.
Tell something, whatever you are feeling.
So I'm not sure with the directions, but both the forces, if we take along 2u is equals to, we get some relation with v, sir.
Xavier, what are you thinking?
So I don't know, like I'm still thinking what the relation can be.
See, this string should not break, right? Correct? If you are pulling this down with you, that means
Yes,
each
sir.
Sir, are
particle.
you presenting?
Yes, you are not able to see.
And no,
No,
sir.
sir.
Oh, sir.
All right. See, what I'm saying is, if you are pulling this end with you, correct? That means each particle has to come down with you, right? Correct? All these particles
Yes,
will be
sir.
moving with you, correct? That means this strings, if you see this block, this is moving with V up, correct? And this string is moving with you, correct? Any doubt? Each particle of the string is moving with you, correct?
Yes, sir.
This angle is how much? Theta. So this velocity of the block is contributing how much in this direction along the length? V cos theta.
Yes, sir.
So this should be equal to U, right?
Like, so both
this,
of them are equal.
Yeah, they have to be equal. Otherwise, you are saying, well, this point is moving with different speed and this point is moving with different speed. That means this will break. No. If these two are not equal, then the string will break. What I'm checking is the blocks, this point where the string is touching the block is moving with V up. And the string is moving here with U, correct? Along the string, the velocities are should be same. Since the rope is touching the block, this point is moving up with V and this angle is theta. So the component of velocity along the string is V cos theta and that has to be equal to U. That's what we were doing, right? In the beginning, where is the string constant? That's what I told you here. Any velocity which is contributing, take its horizontal component, and that should be equal to all that will be the same as the string moving. Okay, clear? Clear, guys?
Yes, sir.
Okay, all right. Now you guys tell me this. Let's say there is one pulley now and you have tried two blocks like this. Okay, this angle is theta 1 and this angle is theta 2. This is V1, this is V2. Now tell me what is the relation between V1 and V2. So this point is in touch with the block, right? This is moving with V1. So what will be the component of this V1 along the length? V1 cos theta 1. Similarly, V2 ka component, what will be this along this? V2 cos theta 2. So if you don't want to break it, it should be same. So V1 cos theta 1 should be equal to V2 cos theta 2. Understood? Understood, guys?
Yes, sir.
Yes, sir.
Okay. So I'm writing the statement again. Velocity along the length of this string should be same. Just I'm using this statement in all the questions that I have done. Got it?
Yes, sir.
Yeah. So I think that's it for today. We will see more questions and output machine, pulley problems, all those things. And then once we're done with that, I will give you some questions. And then there will be one exam. And after that, in 1 or 2 days, I will start with next chapter, work power energy. Okay, guys, are we moving properly or you are feeling it's a bit faster or a bit slower?
Sir, it's fine.
It's
It's
going
fine,
good.
sir. Like, yeah, it's
Yeah.
going good.
But you should practice more questions, guys. So you are not raising doubt at all. You should ping me in WhatsApp or
Yes, sir.
so ping me, ask doubts, do more questions. I should feel like, well, these guys are putting their effort, they are working hard. Okay? Bring new questions. We can discuss. I can put my thought and I can give you some easy methods to solve. Isn't it?
Yes, sir.
Yeah, and also Xavier, you ping me in WhatsApp, okay? I don't have your number.
Plus,
And
I'll do that.
yeah, also Samhita, I don't know. Yeah, Samhita, not Samhita J.
Yes,
Samhita,
sir.
actually ping me.
Yes, sir.
So yeah, I'll add all you to a one group where I'll name it as a doubt session. So there you can put up your doubt. Whenever I get time, I solve it and put it in the group. Okay.
Okay, sir.
All right, guys. Then see you. Bye bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.